Well, if you're registered in Mr. Stewart's MCV4U class, this is the right place to be, and this is the right video to be viewing on May the 16th, 2013. Your task today is to follow along with this production, and a grand production it is, of something called the dot product. So this is a three-part lesson, and in the first part, we're going to define the dot product in the context of an example. That is the example of work. So you may have seen this in physics class when you were studying the concept of mechanical work. Parts 2 and 3 are going to relate to more of the other characteristics and other properties regarding the dot product, and then part 3 will involve some application. So let's consider this new operation. It's specific to vectors, and it produces a scalar quantity. Go figure, right? How do I come up with a scalar if I'm working purely with vectors? Well, that's what we'll see today through an example involving work. Now, work, by definition, is the magnitude of a force, let's call it F, applied in the direction of motion. And it's of the object, of course, and that's multiplied by the magnitude of displacement. Displacement is denoted as S, so the magnitude of vector S will give us the magnitude of displacement. The result is, wait for it, a scalar. So the result is a scalar quantity, which makes sense, right? How much work did you do? There must be a numerical value that represents the amount of work that was done. So let's look at an example. We have a mass resting on a ramp at a particular point. We're going to take a force. Let's say that the force, let's give it 50 newtons. Fair enough? 50 Newton force is applied to the mass at an angle of 30 degrees. And that angle is with the surface of the ramp. The ramp is 25 meters long. Determine the work that was performed to move the mass. So, let's check this out. So let's consider this diagram that we have in front of us. This would serve as a really good template for the problem that we're concerned with. So, let's put a few labels on here. We know that this vector here, okay, this is going to be the force that we're working with. So there's vector F. We have an angle of 30 degrees. Okay, and it's important to note that there really are two vectors going on here. Okay, we have this vector, vector F, and we also have another vector. Okay, it's the displacement vector. Okay, so here's S. That's the displacement vector. So to find the work, what we're going to have to do is we're going to need the magnitude of the component of the force along the hill. Okay, so that's a lot of jargon for this here. That's a component, right? So we need that particular measurement right there. So the magnitude of the component of the force that's along the surface of the hill. Okay? So what we're going to do is we're then going to consider a calculation that involves this triangle. And you might remember that triangles, in fact, here's a perpendicular that's being drawn from point B to C. Triangles are very critical in a lot of the math we're doing with vectors because of the trigonometry that's necessary. So let's move forward here and let's do a calculation. Okay, so in blue, if you will, this component that we have down here, let's consider that as, let's use lowercase f here, and that is a component vector, okay, to the vector f. So let's take that and try to figure out what it is. So that particular vector, okay, which is f, we need its magnitude, and also its AC, okay? That in itself is a component. and it's a component to this vector right here. So when we calculated components, especially those that are horizontal, what we would do is we would take the magnitude of the force and we'd multiply it by the cosine of the angle. So in this case, that component force, okay, that's the magnitude of the force along the surface of the hill. Okay, please don't get that confused with the displacement vector. Okay, these are two different things. This one here is the force applied to the object, that is with reference to the surface of the hill, and this here is the displacement vector. So it's more or less the directed distance through which the object is moved. Okay, so let's keep that clear. So we know that the force that's given is a 50 Newton force, and we have the cosine of the angle, and that's 30. Okay, so far so good. That part's done. Recall now that the definition of work as given over here is the product of these two. Okay, so this mechanical work here, this variable here, although was written down as uppercase F in our example, okay, it is that particular vector, or that the magnitude of AC. The large F was simply used to represent force in general. It did not mean the component force. So I just want to make that sure that's clear as well. So let's move forward and calculate work. So work then is going to be the magnitude of that force that's applied, okay, in the direction of displacement, okay? So let's make that clear. Work is done in the direction of the displacement. So we need to take the value of that component vector, its magnitude, and we have to multiply that by the displacement of this object. So we've already calculated this. It's 50 cos 30, and we'll multiply that by the magnitude of the displacement. So in this case, I believe it was a 25 meter long ramp along which this object is moving. And if you calculate that, okay, I think I had that here earlier on. I had my calculator out. I was just checking some numbers. It worked out to be 1,082. So we'll round that up to 1,083 given the 0.53. So we've got approximately 1,083, and that would be whatever units. In this case, the units are Newton meters. Okay, force applied through a distance. This is also, the units are joules, so that is in uppercase J. Okay, let me take that approximation symbol out here, and we'll fix that up. So 1,083 joules is the amount of work that has been done to move the object through that distance of 25 meters. So what you have just done is you have applied what is called the dot product. Okay, so this thing here, work, this is an example of something called the dot product, okay, of two vectors. In this case, our two vectors were these ones that were given. So vector F and vector S, okay, and the component vector here was necessary to allow us to solve or apply what we call the dot product. So from your textbook, page 371, as you can see here, McGraw-Hill Ryerson provides us a summary of what the dot product is. So the dot product, let me highlight this here, is here, okay? So notice the notation that's used. There is an actual dot in between the vectors A and B, and as you can see, we take the vector A, which in our example was displacement, you multiply it by not just the vector b, okay, which is here. That was our 50 Newton force in the example, but rather you multiply it by b cos theta. Okay, so b cos theta is somewhat of a, if you will, is a projection. Okay, it's a projection of this particular vector here onto this vector here. So b cos theta multiplied, you can see they're multiplied here together. And that represents what we call the dot product. Other things important to know, vectors are arranged tail to tail. The domain here of theta will be 0 to 180 inclusive. And the dot product is a scalar, okay, not a vector. And the units depend on the application. So track the units you're using. What are the two quantities being multiplied? In this case, Newton meters resulted in units of joules. So to make sure that this was okay and this is sitting well with you, what I would ask you to do is to read over example 2 on page 371 of your textbook, and then give numbers 1 and 2 a shot. Okay, part 2 will follow up tomorrow. I'm going to have you work on that and applying the dot product to particular, how should I put it? It'll be more investigation based, more hands-on, so that you can see other properties of the dot product.